So now let's start with the, this is 21, 4-3 TK. So we're going to start with this one. So the first thing is, this is, I'm going to do the paper in reverse. So the first question is about, it's about carbon-13 NMR spectrum of A contains 6 peaks. So what does that indicate? It indicates that there are in C8H8O2, that indicates that there are 6 different types of carbon or 6 different chemical environments.
So,
yes.
Which paper is this?
This one is 21 question paper 4-3.
Okay, sir.
So there are 6 different environments for carbon. So there are 6 different ways that the carbon atom is bonded. And now the first thing is that if you look at this molecule, what you'll notice is that the carbon and hydrogen ratio is almost one. It is exactly 1:1. That kind of indicates that there must be a benzene. Because remember, in all other compounds, the carbon to hydrogen ratio is at least 1:2. Like in alkenes, it's CnH2n, which means the hydrogens are double the amount. In alkanes, it's CnH2n plus 2. It's more than double. But it's 1:1 only in benzene. So the first thing is, whenever you look at a molecule and the carbon to hydrogen ratio is almost the same, that indicates that it is a benzene. So at least 6 carbons are involved in a benzene ring. Then compound A reacts with excess of bromine water to give compound B. So we know it's a benzene, but it's a benzene that's reacting with bromine water. So I'll just quickly do a revision of which benzenes actually react with bromine. So here's the board, and remember electrophilic substitution of benzene or arenes. It's kind of the same thing. So you've got arenes over here. Arenes and benzene almost have the same reaction. So they react with bromine, but they react with bromine in the presence of a catalyst, not otherwise, because the benzene ring is not that activated. So you've got nitration of benzene as well. So remember, for bromination to happen or chlorination to happen, you need an FeBr3 catalyst. But there is an electrophilic substitution of benzene that happens without a catalyst, and that one is this one, when the benzene is very activated. So it's the electrophilic substitution of phenols and phenylamine. So it's, in that case, it's highly activated. So the lone pair on the benzene overlaps with benzene's pi-electron cloud, and so it overlaps with benzene's pi-electron cloud, and the electron density increases on the positions 2, 4, and 6. So, and in amines as well, phenylamine, the same thing happens. The lone pair mixes with benzene's electron cloud, and the electron density is very high on the 2, 4, 6 positions. So in this case, bromine doesn't need any catalyst. The electron density is so high that the electrophile gets attracted to it very strongly. So you should remember all of this. That remember, one thing is, I'll just quickly go over the revision of all these benzene related compounds. So let me just revise this quickly. So the first thing is, you should know about the mechanism of benzene reacting with bromine. It doesn't react without a catalyst because the bromine molecule is not polarized enough, because the electron density in a benzene is very distributed. And when it is very distributed, it's not able to polarize the bromine molecule. So you need an iron catalyst on the other side, which does the remaining polarization. It pulls the electron from the other side. Whereas the electron cloud over here, it pushes the electron to the other side. So when this bromine positive ion is formed, it quickly pulls an electron from the benzene. So the benzene carbon atom over here has an electron cloud missing, because the electron got attracted to the bromine. So the electron cloud becomes partial, and in the next step, the H gives away the electron, and the electron cloud becomes complete again. But and the H leaves and bonds with this bromine, and HBr is formed. So that's the mechanism, and this is the mechanism that you're going to draw, the same mechanism that you're going to draw in the paper. So that is bromination, but that bromination does not happen without a catalyst. When you have 2,4,6 directing groups, which are electron donating groups, so benzene can come in all sorts of shapes. So when you have an electron donating group, like an OH group, the electron density becomes greater on one side, on the 2, 4, and 6 position. So these were some of the groups that were 2, 4, 6 directing. You could have an NH2, an NE-amine, NOH. It could be an amide as well, could be an alkyl chain, or could be a Cl atom as well. So all of these are electron donating groups, and they increase electron density. With adenes, the electron density does increase, but not enough. So the conditions are kind of the same, except for the fact that the bromine is going to get attached to position number 2 or position number 4. But in the case of phenol and phenylamine, the electron density is really high. So the bromine gets attracted to all 3 positions, and you don't need a catalyst. You just Br2 aqueous would be enough. DK Sohail, is this clear?
Yes, sir.
So, so remember this, Br2 aqueous. But if I go back to the question, so my hunch is, like, it's reacting with bromine water. So my hunch is that based on this benzene might be a phenol. But remember, it's got more carbon atoms than that. It's got 8 carbon atoms. So it might be a phenol, or it might just contain an alkene group, your plain old alkene group, because that will also react with. That is also going to react with bromine water. Now, the next one is it reacts with alkaline aqueous iodine to form a yellow precipitate C and compound D. So what is alkaline aqueous iodine? That's your iodoform test, which is shown over here. So that is your iodoform test at the bottom. The iodoform test is a specific test for 2 specific structures, which is could be a methyl next to acetyl bond, or it could be a methyl next to CHOH. So it's a test for these 2 structures. So you're getting a positive iodoform test. So what we're going to write is, based on the iodoform test, you're getting a yellow precipitate, C. The yellow precipitate is of CHI3. If I go back, the yellow precipitate is of CHI3. The CH3 breaks off and turns into triiodomethane. The other part of the molecule actually turns into a carboxylic acid. So coming back to this, I got a yellow precipitate and compound D. So alkaline aqueous iodine. What does that indicate? It indicates that it must be a methyl with acetyl bond O, or it might be a methyl with a CH and NOH. The next part is it reacts with PCl5 to form compound E. So it's reacting with PCl5 to form compound E, which is this one. Now, compound E, that means now PCl5 is known to react with or to change the Cl. The OH group gets replaced by a replaced by a Cl. But he's talking about compound D over here, not the original molecule, which is A. And then he says compound E reacts with, what is E? Where did E come from? Actually, E is this one. Then he says compound E reacts with propan-2-ol to form compound F. Now remember, what is E? E is a carboxylic acid, because after the iodoform test, what you're going to get is a carboxylic acid, a salt of the carboxylic acid. That's what you're going to get, because the conditions are alkaline. So you're going to get a salt of the carboxylic acid. So when he talks about E, when he talks about D, so he's saying it reacts with alkaline aqueous iodine to form a yellow precipitate and compound D. So it would be compound D over here is probably going to be a carboxylic acid, or it's salt, since you're using alkaline conditions. And D then reacts with PCl5, so the OH gets replaced by Cl. OH gets replaced by Cl because of that. and then this one's. अच्छा ये सॉरी कॉल आ गई थी. अच्छा coming 1 second. Can you hear me? Hello.
Yes.
Acha, coming back to this question, you got lots of things going on over here. So, compound E reacts with propane 2-ol to form F, which is probably an ester because this, I think, is an acyl chloride. So it must be an ester. So I'll just briefly outline what's happening here. The first thing is there was a compound A, and that was benzene, and then I figured out that it's reacting with bromine water. So that kind of indicates that it because benzene only reacts with bromine with a catalyst. So when it reacts with bromine water, so that gives me an idea that it might be a phenol, or it might contain an alkene group because you've got 8 carbon atoms. But the thing is that it's probably not an alkene because it's got these other groups. So the other remaining carbon atoms that are not part of benzene might be in these two forms. Might be this or might be this. Now I can kind of sketch what this benzene would look like. So I'm going to do this over here. So for example, over here, I know it's a benzene, and my hunch is that it's a phenol. Why? Because it's got bromine. Plus, it's got a positive iodoform test as well. So it might be a CH3 serial bond O, or it might be a CH3 CHOH. So it could be both of them because you're getting an iodoform test which is positive. So it might be, let's go with this one first. Now he gave us the molecular formula of this thing. The molecular formula was C8H8O2. So that was the molecular formula, C8H8 and O2. So I'm just going to try and figure this out. Do I get C8H8O2 with this? So these would be my hydrogens. Every carbon atom in benzene is bonded to one hydrogen at least. Now over here, you've got different groups attached. Now, if you look at the carbon atoms, that's 8, 1, 2, and that's 6 of them over here. So that's 8, that's fine. Look at the hydrogen atoms. That's 1, 2, 3, 4, 5, and 3, 8. So it must be a methyl ketone because if I go with the other one, it's going to have 5 hydrogens. So that would exceed the number of hydrogens, and there are 2 oxygens. So my hunch is that it's probably this molecule. The only doubt I have now with this molecule is, the only doubt I have with this molecule now is, I'm pretty sure it's this molecule, but the only doubt I have is the position of the OH group. I am not really sure what exactly is the position of this OH group. Mohammed, is this clear?
Yes, sir.
I said, then he says he had this molecule, and then he says that it reacts with what? He says that it reacts, A reacts with alkaline aqueous iodine, and so there's another thing that he's saying compound A reacts with bromine to give compound B. So 2 bromines getting added. So remember, OH is an activated benzene. So when it reacts with bromine, 2 bromines are going to get added at positions 2, 4, and 6 because it's activated. So that is what is going to happen. So that is this molecule, the reaction with bromine. This is what's going to happen. And you're going to get exactly the formula that he's quoting. He's quoting C8. 2 hydrogens go away, replaced by 2 bromines. So 2 of the hydrogens that were with bromine, they go away. The next is the iodoform test. So the iodoform test is CH3 breaks off. So that is CHI3. You can just hold on 1 second. I'll just. So this is the iodoform test. Just hold on 1 second. Just 1 minute. So let's continue with this. Then the last part was over here, because he's reacting D with PCl5. I'm just assuming that he's not talking about the salt because he's talking about the carboxylic acid. Remember the iodoform test. The iodoform test produces a carboxylic acid that turns into a salt because the conditions are alkaline. But in this case, because he's immediately reacting it with PCl5, so I'm assuming that it's probably not a carboxylic. It's not the salt that he's talking about. He's talking about the actual carboxylic acid. And then this OH gets replaced by Cl. So that is what is happening here. And you have to draw these things over here. So we did draw some of them. Now he's talking about the yellow precipitate, which is CHI3. So I'm going to quickly, this is this molecule over here. This molecule is, I mean, what is this molecule? It's the same molecule, except these two positions are going to be bromine. This other part is this one. The Cl, when the PCl5 comes in, the role of the PCl5 is to replace the OH in alcohols as well as carboxylic acid with Cl groups. So E is this one. And then you have to draw F. F would be that an ester would be formed. That this molecule, the one that's above, that's with the Cl and an OH over here. And it's reacting with propan-2-ol. Propan-2-ol is that the OH group is in the middle chain or on the middle carbon atom. So what will happen is that the Cl and the H are going to be lost and they're going to form HCl. And the two molecules are going to link up. Remember, acyl chlorides are the ones that form esters. And they're very good at forming esters. So F is going to be an ester. That's what F is going to be. Remember, esterification happens by two compounds. One is you need a carboxylic acid reacting with an alcohol, and the H and OH would be lost. The other one is you could have an acyl chloride that would react with an alcohol. And in that case, HCl, an elimination reaction would happen, and HCl is going to be formed. And an ester would be formed. Acyl chlorides are better at forming esters. Why? Because acyl chlorides are also capable of forming esters with phenols. They can form esters with alcohols. They can also form esters with phenols as well. So is this clear? This is your final molecule. Sohail, is this clear?
Yes, sir.
Now the next one, now how did I figure out that the OH is on this carbon? Remember, you can actually even figure that out. So my only question was, how did you figure out that OH is on this carbon atom and not on any other carbon atom? Now he gave us a hint over here. He said that the carbon 13 NMR contains peaks, and there's 6 different environments. So it's going to be this one, because if you look at the carbons over here, then that's one environment, because that carbon is different from all the other ones. These two carbon atoms over here are kind of identical. So that's the second environment, that's the first environment. These two carbon atoms also are in identical environments, so they're exactly the same, and they would resonate at exactly the same frequency. Then you've got this carbon atom, and you've got this carbon atom. So how many different environments do you have? You've got 1, 2, and sorry, I missed one carbon atom over here. There's this carbon atom over here as well. So that's a total of six environments. If the OH was at any other position, you'll get more environments like if I draw a molecule, same one, except that the OH is at a different position, like this one. Now, what will happen in this case is these are all hydrogen atoms. Now, what will happen in this case is you're going to get a different number of chemical environments for carbon. That's one. This carbon is different, so that's one. Remember, this carbon is different from all the other carbon atoms because none of them are similar to this one. This CH3 is different, this carbon is different, this carbon is also different. This carbon is different from all the other ones. So all of these carbons are kind of different from all the other ones. They're not, I mean, there are no similarities between them. For example, this carbon is bonded in a different way. This carbon and its neighboring environment is different from all the rest. But over here, these two carbons kind of had exactly the same chemical environment. So over here, you're going to get more peaks. Mohammed, is this clear? Danish, is this clear?
Yes, sir.
So remember, when you talk about environments, the carbon has to be bonded in exactly the same way. If it's bonded and its neighborhood must be exactly the same. So these two carbon atoms are exactly the same. So they're going to resonate at exactly the same frequency. So there would be 6 peaks. But over here, all the benzene carbon atoms, all of them are slightly different from the other one. This one is different. I mean, no other carbon atom has the same environment as this one. So which is why you're going to get more than 6 peaks. So moving to the next question, you've got this question which says that I think I've done that. I'm going to try. We probably did this one. So I just try and open a different paper. Just 1 second. Actually, this one is the same. Just a second. This. So let's try and do this one. Question number 10. He's saying predict the likely oxidation states of predict the likely oxidation states of element Q in its compounds. You're given this element. So first thing is, what is this element? You got 3D2 and 4S2. So it's probably the one after scandium. You can remember, you have to be quick with this. Where's the data booklet? Remember, make sure you know how the electronic configurations work. Up till calcium, you got 4S2. Then this is 3D1, this is 3D, this is 3D2. So he's talking about titanium. For titanium, the likely oxidation states are +2. And you can go with +4. So titanium has these two likely oxidation states of compound Q. So you can write one of them. If you're confused, you can even look for titanium in the data booklet, which I don't think it would be given in the data booklet. But whenever you're confused about oxidation states, what you can do is you can open the electrochemistry table. But over here, I don't think titanium would be present over here. No, it's not. So for titanium, make sure you remember the most likely oxidation states for titanium. Now, suggest why transition elements often show variable oxidation states in their compounds, but typical S-block elements such as calcium do not. Now, the reason for that, the simple reason for that is that the 3D subshell and the 4S subshell, the energy difference is very little. So there's less difference in energy levels between the outer 4s. So between the outer four, this one is Medium 24.3, summer 24.3. So levels between the outer 4s and the inner 3D subshell. So the energy difference is not really very high. In calcium, the energy difference is very high because after the 4s, like if you look at calcium's electronic configuration, you reach 3p6, and then all of a sudden you have 4s2. So the energy difference is huge in this case. Now, many enzymes contain transition element complexes. Describe with the aid of a suitably labeled diagram how an enzyme catalyzes the breakdown of a substrate molecule. Now, for this, you have to draw the lock and key model. So I'll just show you, instead of drawing, I'll just show you the picture of a lock and key model that what you have to draw is, let me just show that in the marking scheme. You have to draw an enzyme, an active site. You have to draw the substrate on which the enzyme is going to work on. And then they're going to combine together and the substrate will. So hopefully they have it somewhere in this one. So you can draw a rough diagram. And remember, it was, I think the marks were all for the diagram in this case. So you have to show an active site, you have to show a substrate, you have to show an enzyme. You got an enzyme substrate complex, and then the substrate breaks down into its products. So these three things need to be shown. And that's it. They're not going to ask you for any other explanation for this, except for this diagram. That diagram has to be remembered in this case. Now, in this, you have to describe how an enzyme catalyzes the breakdown. So you have to describe that as well. So you have to talk about the complementary. So I mean, they were asking for the how as well. So you have to describe the complementary shape. It's basically the same thing. Just describe what the diagram is doing. The substrate binds to the active site. The enzyme then breaks down the substrate, and products are released. Now, the other question is, okay, let's move to the previous question now. Now, this one is, you've got manganese MnO2 catalyzes the decomposition of hydrogen peroxide as shown. The mechanism involves the formation of the intermediate Mn2 plus, the first step, which is subsequently used up in the second step. State and use the relative electrode potential to construct two equations to show how MnO2 can catalyze this reaction. So he has given us some hints, and those hints are that there's MnO2, and it turns into an intermediate, which is Mn2 plus. So what we need to find is, we need to find an equation in the table which involves MnO2 and it's turning into Mn2 plus. So quickly open the data booklet, and over there you're going to find an equation of MnO2, which is this one, MnO2 plus 4H plus 1, gaining electrons. So it's MnO2 plus 4H plus 1 plus it's gaining electrons, turning into Mn2 plus I think H2O. And I can check the numbers. So it's this one. 2 H2O, 2 electrons, 1.23 volts. So 1.23 volts, 2 H2O, 2 electrons, and this one is 4H plus 1. So this is one of the reactions. Now, what is it going to react with? He's saying the mechanism involves the formation of the intermediate species Mn2 plus. And the first step, which is subsequently used up in the second step. State and explain the relative E0 values to construct two equations to show. So what is the first equation? So it's probably going to react with H2O2. So we're going to go and have a look at H2O2. How many equations do we have for H2O2? And also remember, MnO2 is going to form or gain electrons to form Mn2 plus. That's the intermediate that's happening. So who gains electrons? It's the higher E naught that ends up gaining electrons. Remember the first step. You added MnO2, it turned into Mn2 plus. He already said that. The intermediate is formed. And just to be careful, make sure you have no other reaction where this is happening. You don't have MnO2 anywhere else where it's turning into Mn2 plus. You don't have an equation for that. So that's the first step that's happening. What is it reacting with? The only thing that's present is H2O2. So H2O2 is the one that must be losing electrons, because MnO2 is definitely gaining electrons to form the intermediate. So find an equation where H2O2 is losing electrons. So we need H2O2 to be on the right side if we have H2O2. So we need to find H2O2 to be on the right side. So I've got one over here. That's probably the only equation I have. I wanted to lose electrons. So I'm going to write this O2 plus 2H plus 1 plus 2 electrons. So I've got O2 plus 2H plus 1 plus 2 electrons in equilibrium with H2O2. And the value for that is 0.68 volts. So that kind of works out as well, because that is the lower E naught. Remember this, in electrochemistry, it's the lower E naught that always loses electrons, and it's the higher E naught that always gains electrons. So the lower E naught is the one that's going to lose electrons. So I'm going to just recap how I did this. He told me that MnO2 is taking part in the reaction and it forms an intermediate, which is Mn2 plus. So I opened the data booklet, I found an equation where MnO2 is turning into Mn2 plus. And I know that it's going to go in the forward direction. It's going to gain electrons. And I know that whoever gains electrons is the one that has the higher potential. So we figured out who's going to gain electrons. The only thing that's present over there was the one that was going to lose electrons, which in this case would be H2O2, because that's the only thing that's present. So I found an equation where H2O2 is losing electrons, so it must be on the right side, so that in the reverse direction it loses electrons. And so that is the one that loses electrons. Okay, Mohammed, Danish, is this clear? This first part?
Yes, sir.
Yes, sir.
And then after that, what is needed is, like, that's the first reaction. Now, what happens after that? I mean, you need to construct the first equation now. The first equation is going to be just add up the reactants. So I'm going to add up the reactants, which in this case would be H2O2. That's the reactant. The electrons need to be equal. The electrons lost and the electrons gained, they need to be equal. So add up the reactants. So that's one of the reactants. What are the other reactants? You got MnO2 and you got 4H plus 1. And now add up the products. If you add up the products in the first one, it's O2 plus it's I think 2H plus 1. And at the bottom, the products are Mn2 plus 2H2O. So those are my products at the bottom. And
Sir,
and what? Yes.
we're taking H2O2 in the reactant side because it's losing electrons.
Okay. I mean, this reaction is going in the backward direction. TK, lower potential, remember, always loses electrons. Whenever you have a lower potential,
so that's why we'll take it in the reactant side.
Because it's going in the backward direction. TK.
Yes.
Or how did I figure it out? It was losing electrons because they told me that MnO2 is turning into Mn2 plus, so that is gaining electrons. So the other one must be the one that would be losing electrons, which is why I specifically found the equation. Because remember, if you look at the data booklet, H2O2 might be on the left side as well. Like if you look carefully, I mean, you might find H2O2 somewhere on the left side as well. Just a second, if I can.
Yes,
I mean,
sir, Cooper. H2O2 plus 2H.
But I can't, because that would mean that H2O2 is gaining 2 electrons to form this. So, I mean, I'm not going to take that because he already told me that MnO2 is the one that's that's gaining electrons. So H2O2 is the one that must be losing electrons. So it must be on the right side. Okay.
ठीक है sir.
Achha, so I found the first equation and I'm going to try and simplify this. So it's going to be, I mean, only the H plus ones are going to get cancelled out. So the H plus one over here are gone, and over here, the H plus one are gone. And I'll be left with just 2H plus one, that's it. So that's my simplified equation. That's the first reaction. I'll just copy this again, Mn2 plus 2H2O. Now the next part, what is the other reaction? Because remember one thing, we found the half reaction, the first one, which is this one. This is the first reaction that's happening. Okay, that's step number one. We figured that out. Now I need to figure out step number two. How do I figure out the second step? Remember, he's saying state the construct two equations. So H2O2 is turning into H2O, and it's also producing oxygen. But what I need to do now is I need to convert the Mn2 plus back into MnO2. I need to do that. I need to convert the Mn2 plus back into this. So what could be this other reaction? This is the one that I need to find out. What's this other reaction that I need to use to convert that back into MnO2? That is what we are looking for. So this other reaction is this one. What you can think of is there are two ways of doing this. Here's your overall equation, this one. Remember, there's this step number two. We don't know what this step is. So right now, we don't know what this other step is. But I know that if you add up the two steps, I should be able to get this overall reaction, which is 2H2O2 turning into 2H2O plus O2. So think of it this way. We figured out the first step, just the first step, because he gave us pretty much all the information for the first step, right? So I figured out the first step, but he said that there were two equations. There was a second step as well. But what I know of is I know the overall reaction. This is the overall reaction that he gave me. He told me some information about step number one, and I have no idea what step number two is. But remember, step one and step two are going to add up to form this overall reaction. Is this point clear? Danish, Sohail, is this clear?
Yes, sir.
Yes, sir.
Okay, so remember, if a reaction has multiple steps, you add up the steps and you get the final overall equation. So you found the first step, we have the overall equation. So I'm going to try and find the missing step. So what I'm going to try and do is, remember, it's simple addition, simple math that's happening. So what I need to have over here is, and this is, sorry, H2O2. Okay, this is H2O2. The first thing that's missing over here is if I'm going to add step number one with step number two, it should give me 2H2O2. So what is missing? There is one H2O2 that's missing. Is this point clear? I mean, is this point clear?
Yes, sir.
I said that's missing. Then MnO2 should not be over here because there is no MnO2 over here. So what is missing? It must be minus MnO2. Okay, that is, I mean, you need to subtract it somehow. And you also need to subtract the H plus one because there is no H plus one, right? I said, what about over here? The two water molecules, that's fine. That should be here. And you got an oxygen molecule that's also here, but there should not be any Mn2 plus. So you don't need that over here in this particular step. You don't need that. So I need to subtract the Mn2 plus. I mean, the second step would be the one where the Mn2 plus is going to get used up. It's going to get subtracted. So is this point clear what I'm doing over here? I'm trying to find out the missing step because I know the step number 1 and step number 2, they add up to give me this step. So there was only one H2O2 on the left side. So I needed two H2O2 molecules. So I added another H2O2 over here. There was an MnO2, but there was no MnO2 in the overall equation. So that must be getting subtracted over here. There was H+1 over here. There's no H+1 in the overall equation. So that must be getting removed over here in the step number 2. There's oxygen. So I kept the oxygen, didn't subtract it. There's H2O, I kept that. Mn2 plus, no Mn2 plus in the final. So that must be getting subtracted. So is this point clear so far?
Yes, sir.
All I need to do now is rearrange this, because in your equation, just like a math equation, you don't have, in an equation, you just have plus, you don't have minus. So how can I convert the minus to plus? All I need to do is take the 2H+1 to the other side. Take this minus Mn2 plus to this side. So what I'm going to do is I'm going to put it over here. So it would become plus Mn2 plus. And this MnO2 will be taken to the other side. So minus MnO2, the other side it goes and forms plus MnO2. So just like a math equation, I just rearranged it. So I just get positive values, and I'm just going to check if this is balanced. The oxygen is balanced, the Mn is balanced, and the hydrogens are also balanced in this case. So that is how I've been able to, by subtracting the overall equation in step number 1, I've been able to figure out this missing step as well, which I think is given over here. This one. Right? This one was a difficult question. You usually don't get questions like these. So is this point clear? How we did that?
Yes, sir.
Yes, sir.
And what you can now do is, once you know what the second step is, because I think we didn't read the question properly, but in the marking scheme, how are the marks distributed? Anyways, the E0 values you're not supposed to calculate. That's 1 mark for this one, 1 mark for this other one. The only thing that you can now do is for this particular step, and that's mark one for, yes, for this one. Once you've figured out, so there's 1 mark for this. Once you've figured out this particular step, this one over here, all you have to do is you have to calculate because he was talking about the electrode potentials as well. So you're going to open the data booklet and you're going to try and figure out which 2 equations actually make this step. So open the data booklet, it's 2 equations. One is Mn2 plus turning into MnO2, which is basically the same equation, the one that we quoted over here. It's just happening in reverse. Mn2 plus turning into MnO2. The other one is H2O2 turning into H+1. So I need to find that one. Remember, it's pretty easy now. Mn2 plus is the one that's losing electrons now. So I want an equation where H2O2 is gaining electrons. So if I look at the data booklet, I want H2O2 to be gaining electrons. So it's probably this one, because I think there's only one equation where H2O2 is gaining electrons. And I want MnO2. Sorry, I want, if I go back to the paper, I want Mn2 plus to be turning into MnO2. So I want Mn2 plus to be turning into MnO2. It's this one. So this is the lower potential, 1.23 volts. And the other one is the higher potential, which is 1. If I can put them together, you have your 2 equations in front of you. You want Mn2 plus to turn into MnO2, and you want H2O2 to turn into, to gain electrons. And there's only one equation. If you add up the 2 reactions together, it's going to get simplified. We can simplify this. The electrons are already balanced. Remember, the electrons are already balanced. I can do the math over here. This is my reactant, so that's Mn2 plus. plus 2H2O. What are my other reactants over here? It's H2O2 plus 2H plus 1. And my products are, in the first one, it's MnO2 plus 4H plus 1. And in the second one, the product is MnO2 plus 4H plus 1. In the second one, the product is 2H2O. Now, if I start balancing this, the 2H2Os will get cancelled out. The 2H plus 1 over here will get cancelled out, and you'll be left with just 2H plus 1 on the other side. And that is exactly the reaction that you got. You got Mn2 plus H2O2, and the products are MnO2 plus 2H plus 1. And you can find the E naught value. It's higher potential, which is 1.77, minus the lower potential, which is 1.23. The lower one is the one that's going to lose electrons. The higher one is the one that's going to gain electrons. But remember, the easy way, we were able to figure this out because we were able to figure out the equation before we actually figured out the electrode potential. Because it was pretty hard to actually figure out the second reaction by just looking at the electrochemistry table. So we did the reverse, we did the opposite. What we did was, he gave us information about the first step. So we figured out the first step. He gave us information that MnO2 was turning into Mn2 plus. So I figured that out, MnO2 turning into Mn2 plus. I found that equation. And I know that if it is gaining electrons, then H2O2 is the one that must be losing electrons. So I made up the first step. When I had the first step and I had the overall reaction, I was able to figure out what this missing step is. Once I figured out the missing step, it became kind of easy to look at the electrochemistry table because I knew that Mn2 plus is turning into MnO2. And so I figured that one out, that Mn2 plus is turning into MnO2, so it's losing electrons. So H2O2 is the one that must be gaining electrons. And I was able to figure this equation from the electrochemistry table as well. Is this question clear?
Yes, sir.
Okay, Sohail, is this clear? Adam, is this clear? Remember, this one is a difficult question. Most of the time, the questions that you're going to get are going to be very straightforward. This one was a difficult one, but make sure you know how to do that. Most of the time, the question that you're going to get is, they'll give you the reaction. That is an easy part. Like, for example, they might give you a reaction where they might ask you about this reaction and reacting with, let's say, iodine. So you would realize that higher potential gains electrons, so it's going to gain electrons, and this is the lower potential loses electrons. So you got reaction number one, which is the reduction reaction. Higher potential gains electrons, and you will have an oxidation reaction. You'll just add up the two equations up, and that's going to be your final equation. But sometimes they'll give a more difficult question. They'll give you the final equation, and then they'll ask you to do the reverse. The reverse part is kind of more tricky. It's trickier. Okay, is this clear? All clear? Mohammed, is this clear?
Yes, sir.
So now the next one is the equation for the decomposition of hydrogen peroxide without a catalyst is shown. Under certain conditions, the reaction is found to be first order with respect to H2O2. With the rate constant K is this, and calculate the initial rate of decomposition. So there's only one reactant. Remember, rate of reaction depends on the concentration of the reactant, which in this case is H2O2. And he already told us that it's order 1. To get rid of the proportionality sign, you have a constant, and they gave us the value of the rate constant as well. So all you have to do is you've got to plug in the values and you'll find the rate. The K value is already given. It's 2 times, I think, 10 to the power minus 6. And you need to plug in the concentration of H2O2, which is 0.75, and that's it. You'll find the initial rate of the of the reaction. That's it. So remember, in this reaction, you just had to plug in the values. There was rate was only dependent on H2O2 concentration with the order was 1. Now he's saying a 4-step mechanism is suggested for the reaction between H2O2 and iodide ions in an acidic solution. Step 1 is the rate determining step. What is the rate? What is meant by the term rate determining step? The rate determining step is the slow step in the mechanism. So he's saying step 1 is the slowest. Remember, the rate of the reaction depends on whatever is involved in the slow step. So that means rate depends on these two reactants. Rate depends on H2O2 concentration and I-1 concentration. And both of them would be order 1. So because the first step is the slow step, so rate is going to depend on your slow step. And your slow step would involve H2O2 as well as I-1. Is that clear? Yes or no? Is this clear?
Sir,
Yes.
Yes.
so is it possible that they give the final equation and then they ask to find the rate determining step?
Yes, they will. I mean, they will. I mean, for example, they won't tell you this one is the slow step, right? Maybe some other step is the slow step, right? Now, remember, if let's say the last one is your slow step, right? So how would your orders change? Remember, the reaction is between two things, H2O2 and iodide ions in acidic solution, right? So that means rate depends on either of the three or all three of them, right? And it could be order 1, 2, or 0. So if the last one is the slow step, so I'm just assuming, let's say the last one is the slow step. So your rate equation, your rate would be dependent on the concentration of OH ions, and it would be dependent on the concentration of H+1, right? But then you have to trace back everything, trace everything back. OH-1 is an intermediate. It's not your initial reactant. OH-1 is an intermediate that was formed. When was it formed? When HIO and I-1 reacted. So that means the rate indirectly does not depend on OH-1 because OH-1 itself is formed when I-1 and HIO react. So I'm going to replace OH-1 with HIO and I-1. Is this clear? That if the last step, step number 4, is the slow step, then rate depends on OH ion concentration and it also depends on H+1 concentration.
Yes,
but OH-1 is an intermediate. So that means rate indirectly depends on I-1 because if their concentrations are high, then OH ion concentration is going to be high. So that means rate is not actually dependent on OH-1, it's indirectly dependent on HIO and I-1. But then when I say that rate depends on HIO itself is an intermediate that depends on H+1 and IO-1. So I'm going to cut out HIO because when I say that rate depends on HIO concentration, HIO itself depends on IO-1 and H+1. So I'm going to replace that with H+1 and IO-1. But then when I say that rate depends on IO-1 concentration, I figure out that IO-1 itself is an intermediate that depends on I-1 and H2O2. So I'm going to cut out IO-1 because that's an intermediate that depends on I-1 and H2O2. So that's my final rate equation. So rate depends on all of these things. I removed OH-1, I replaced it with HIO and I-1. Then I figured out that HIO itself is an intermediate that depends on H+1 and IO-1. And then I figured out that IO-1 is an intermediate that depends on these two things. If I bring the terms together, my rate equation would be H+1 appears twice, so it's order 2. I-1 appears twice, so that's order 2 as well, and H2O2 only appears once. So remember, whichever is the slow step, your rate equation is going to change accordingly. In this case, it's the first one. I mean, in this case, he's talking about the first one. But remember, you might get questions on this, and they might give you an order of the reaction, and they'll ask you to figure out which one is the slow step. Mohammed, is this clear?
Yes, sir.
The next one is use this mechanism to construct a balanced equation for the reaction. So just ignore this part. This is the actual first step. So make a balanced equation. The way you're going to make a balanced equation is just add up all the reactants, add up all the products, because we need to make an overall equation. So it's a lot of things. Start canceling things that are common on both sides, because they're going to get canceled out anyways. OH minus 1 gets canceled out. What else would get canceled out? I don't think. So it's basically H2O2 plus, I think, 2I minus 1, and there are 2 H plus 1 ions. And the product is H2O2, sorry, H2O, and the two of them, I think, plus I2. So is this balanced or not? I mean, the water molecule, I mean, this one is H2O2, so now it's balanced. I mean, this is H2O2. So this is your overall rate equation. Is that clear?
Yes, sir.
And he's saying reduce the order of reaction with respect to each of the following. So the first step was the slowest. So it depends on H2O2. I'm always forgetting the 2. So that's order 1. Depends on I minus 1, but there is no H plus 1 in the slow step, so that's 0. The first step was the slow step. He told us the first step is the slow step. So the H plus 1 is not involved in the first step. So if you want to speed up the first step, H plus 1 has nothing to do with that. So that order is 0. And that's it. Now the next one is your dissociation constant. Explain what is meant by the term buffer solution. Remember that. I'll just give you a brief background. A buffer solution is made up of, it's going to resist a change in pH. So instead of the definition is that it is a solution that is formed between a weak acid and its conjugate base, and it resists a change in pH when a small amount of acid or alkali is added. But only a small amount. So I'll just briefly outline how buffers work. For a buffer, you need a weak acid like ethanoic acid, and you need its conjugate base, which is going to be ethanoate ions. You need your ethanoate ions, which are the conjugate base of a weak acid. What's going to happen is one of them is going to act as a base. The other one is going to act as the weak acid. As soon as you add H plus 1 ions, the base is the one that's going to neutralize them. The ethanoate ions, which are usually obtained from the salt, like sodium ethanoate, it will start, if you add all these H plus 1 ions, they're going to be consumed by the base. And as soon as you add OH ions, the acid starts neutralizing them. So the ethanoic acid starts to release H plus 1 ions. And the OH ions turn into water. They get neutralized and you get ethanoate ions. So this is what's happening. You add H plus 1, the base starts consuming them. It starts to remove them. It neutralizes them. You add OH ions, the acid starts behaving as an acid, starts releasing H plus 1 to neutralize the OH ions. Is that clear?
Yes.
Yes, sir.
So over here he's talking about ammonium ions. Remember, ammonium ions can act as a weak acid. They can turn into NH3 and release an H plus 1 ion. So anything that can behave in this way, in this general way, that it produces A minus 1 or some random ion and an H plus 1 ion, that's a weak acid, and it's in equilibrium. So the K expression would be, it would be NH3 concentration over H plus 1 products over reactants divided by the NH4 plus 1 concentration. So it's the equilibrium constant it's the equilibrium constant which products over reactants. So any acid when it dissociates, and remember these two ions are going to be produced in equal amounts. So you can also write the expression as H plus 1 squared divided by NH4 plus 1 concentration. Right? Is that clear?
Yes, sir.
Now, write two equations to describe how a solution containing ammonium ions and ammonia can act as a buffer. Now, you have to understand that ammonium ions are the ones that would act as the weak acid. So if you add OH ions into the solution, the ammonium ions are the ones that would start behaving as an acid. They would start releasing H plus 1 ions that would, this one would release an H plus 1 to neutralize the OH ion. And itself, it will turn into NH3. What if you add an H plus 1? Then the conjugate base, which in this case is NH3, will start consuming that and will turn into NH4 plus 1. So these are the two reactions that are going to happen. Remember, weak acid, it always forms a conjugate base. So that's your conjugate. This over here is this one is the weak acid, that's your conjugate base. The next part is, make sure you remember this. They always, almost in every paper, they ask you for this particular question. Now, the numerical value of Ka for NH4 plus 1 is for NH. They've given us the value for this one Ka. This one over here. So they gave us this value for Ka. And they've also given a buffer solution was prepared. So remember, it's a buffer solution now. Now, there's a thing with the buffer solution, and that is that when you have a buffer solution, you have to calculate the pH of the buffer solution. So the K value is given. So the first thing is, he's saying that 0.8, can anyone tell me what the moles are? Ammonia. How many moles is this? What's 0.8 mole per dm cube? 0.8 into 0.25.
0.2.
So you're getting 0.2 moles. So you had 0.2 moles of ammonia, right? Remember, initially there is no buffer, there's ammonia. And he reacts it with HCl. Tell me the moles of HCl. And ammonia plus HCl is going to produce ammonium chloride, which is NH4Cl, which is basically NH4 plus 1. Cl is 1.
0.04.
So this is 0.04 moles, right?
0.04. Yeah.
So which one is in excess?
Yeah.
So ammonia is in excess. 0.04 is going to react with 0.04. So that means 0.16 moles are left, right? Is that clear?
Yes, sir.
And 0.04 are going to react with 0.04 and they're going to produce 0.04 of this. So 0.04 moles of NH4 moles are going to be produced. So out of 0.2 and 0.04, 0.04 are the ones that are going to react with 0.04. So I'm just going to repeat this. HCl is the limiting reagent, and you have NH3, which is your excess reagent. 0.04 is going to react with 0.04. So that means 0.16 moles are left. 0.04 reacts with 0.04 and produces 0.04 of this. So at the end of the day, you have a buffer. Because the HCl is all gone. Remember, the HCl is all completely used up. So now you have ammonia plus you got a weak acid. This is your weak acid. And that's your conjugate. That's your conjugate base. So remember, you now have a buffer. You've got an equilibrium that would be established between them. The K expression is NH3 concentration into H plus 1 concentration divided by the NH4 plus 1 concentration. So remember, your solution now has two things. One is NH4 plus 1, and it's also got this NH3 as well. So we have the Ka value. we pretty much have all the things now. We have the K value, which is given as 5.6 times 10 to the minus 10. So we have the K value. And then you're given the concentration for NH3 as well, which is 0.16. Remember, this is the equilibrium that would be established between the ions and the molecules that are formed after the first reaction. So we have the NH3 concentration, which is 0.16, multiplied by H+1 concentration and divided by the NH4 plus 1 concentration, which is 0.04. Is that clear?
Yes, sir.
And just make sure, did I make any mistakes over here? You got NH3 at the top, that's this one, the 0.16 moles that are left. At the bottom, you'll have the NH4 plus 1, that's the K expression. And you just have to find the H+1 concentration. So try and find your H+1 concentration now, and you'll find the pH. You take the negative log of that, and you'll be able to find the pH. So is this clear?
Yes, sir.
Yes.
And as I remember about buffer solutions, okay, how are buffer solutions formed? Buffer solutions are formed when you have a weak acid plus its conjugate base in the solution as well. So, for example, whenever you have a weak acid plus the conjugate base is present as well. That is, if two things, both of them are present in the solution, and no matter they come from different sources, doesn't really matter. Like in this case, there was a reaction of NH3 with HCl. The HCl got completely used up, but there was NH3 that was still left at the end of the reaction. And NH4 plus 1 ions were produced as a result. So your solution at the end of the day had NH4 plus 1, and it also had NH3. So you had the same K expression, except that you had a certain moles of NH3, you had a certain moles of NH4 plus 1. So you were able to figure out the pH in that way. So let's try and do more of these questions. I'll probably try and do some questions. Tomorrow I'll have a much longer session, okay? Maybe I'll have multiple sessions. I'm just going to take a break now. Okay. Mohammed, when do you sleep?
It depends.
Yeah, are you sleeping late these days or early?
Yeah, like around 1 or 2.
Okay, so I'll probably, if I get back by around 9:30, maybe we can have another session, right?
Okay, sir.
So, okay, take care. Okay, Danish.
So can I join in?
हाँ ठीक है, you'll have the link. I'll message you, ठीक है?
Thank you, sir.
Okay,
Thank you,
Allah
sir.
Hafiz.